maybe some fill in the blanks. You guys take true and false, don't you?
Waveform strength more.
Okay, I'll make sure that that's pretty straightforward. What all have we covered in here? We talked about the von Neumann machine and processor. I probably asked you a good bit about processors and that fetch cycle. Remember we talked about the fetch cycle and what is it about the von Neumann machine? We talked about the memory and memory addressing and stuff like that. So far, you know, it would be really straightforward. So today is what, 13, 14, 15, 16, that's Wednesday of next week, right?
No.
2 weeks, Wednesday, a week from next Wednesday, right? So 2 weeks from today. So please don't sweat it. Also, that I am new to UCF, so I am always going to land on the side of students, and I will definitely be your advocate, especially since I still don't really know how to use web courses. So anyway,
Professor,
yes.
are you going to make a review sheet?
Mm-hmm.
Okay.
Yeah. And I will give that to you, say, next Wednesday of next week. That way you have a full week on it. And I'll post it on the web course too. So I want to see a lot of really good grades. Okay. So what did we talk about on Wednesday? We talked about numbers, right? And what were the week? And she was telling me that the book was really confusing. Anybody actually read the book?
Yeah.
Was it confusing?
We talk about
Yeah, we're not going to do base 3 or base 4 or base 5 or any of that crap, you know.
sort of Jackson like basically.
Yeah, and third grade math, you know, that's fine, but you're not going to need that, you know, in your job. You're going to need binary, obviously decimal, and hex. So that's why I skip that stuff, because basically my approach to this class is going to be skip the stuff you don't need, even though it might be in the book. So, so we converted from decimal to binary, binary to decimal, decimal to hex, hex to decimal, right? You guys feel comfortable with that?
Yeah.
Not really easy. Good. So one of the things we didn't talk about was that some of these numbers happen to be signed. There was no mention of whether we had a negative or a positive, correct? Okay. So today we've got to tackle that because, as it turns out, it's pretty important. Signed integers. Now, has anybody ever had a programming class like in C? So you have C program. Oh, all of you. Okay. In C, you have these types, right? Int and unsigned int, right? And the int gives you a value of 0 to like 4 billion something, and an unsigned int gives you like a negative, excuse me, a signed int gives you like a negative 2 billion. I'm rounding off, so positive 2 billion or whatever. So that's good. You've already had that. So you know what an unsigned and a signed, you know the difference. But the way it's structured in memory is, imagine, and the ints right now are 32 bits, although, did I mention what the problem with integers in C and C++ programming languages are? They technically go with the CPU size. When I first started programming C++, integers was 16 bits. So they would have a range either from 0 to 65, 535, or negative 32, 768, 32, 767. And the reason is because the processors were 16-bit processors. And then the processors went to 32-bit processors. And I used the next version of Visual Studio, and my apps broke. So theoretically and technically, integer equals whatever the size of the processor is. Now that isn't what happened. But that's kind of the way it's supposed to be. So you have to kind of just keep that in mind. Now, so how big are the integers, if you're going to program in C today, how big are those integers going to be? How many bits? 32 is correct. So where is the least significant bit? I hope I'm doing this correctly. Remember how when we did it before, let's see, yeah, on the right side is going to be your least significant bit. Why? Because that bit is either a 0 or 1, or really a 0 or a 2 in that place, right? That's the value of that place. Now, way on the left side, it's a big value. Let's say if it was an 8-bit value, it'd be 128, and if it was a 16-bit value, it'd be 3768. Okay. But the most significant bit turns out to signify whether the number is positive or negative. Okay, and that's what we use. If it's an unsigned integer, we just totally ignore that. But if it's a signed integer of some sort, then that indicates. So if it's a 0, it's a positive number. If it's a 1, it's a negative number. Okay. And so that's why the signed values have less of a sort of total range, because you lose that bit. And when you lose that bit, you lose another power to the power of 2. Okay. So the remaining bits contain, the actual value. Okay. And back in C++, C, in case you guys just have to say just, it's really good language. You can actually do a bitwise operator and test for that. A lot of times, like the operating system and stuff returns these bit fields, and you have to do a test on that most significant bit. So we're going to talk about 3 ways that these numbers can be arranged. Okay, and 2's complement is the most common, so we get to that last. So in an 8-bit word, really should be an 8-bit byte. We have this representation called sign magnitude. So you have the most significant bit, which indicates whether it's positive or negative, right? And then everything else. No, I was in the wrong side, right? Wrong side. Everything from the least significant bit up to the most significant bit is just the number. Okay? Just as if you would expect it to be. So if it's 8-bit, it'd be 0 to 127, right? And then that most significant bit just is the determining factor whether it's positive or negative. Okay? So really, it's going to look the same with the exception of that most significant bit. In an 8-bit number, let's see, I got to do this. Here's your least significant bit: 0, 1, 2, 3, 4, 5, 6, 7. Okay. Okay. And a 16-bit, you just count over the number of bits, and the very last bit is going to be your most significant bit. The reason it's called most significant bit is because it's the one, if you're doing power of 2, that provides the most value to the number. 2. So take a look. We have a really nice example here. Let's say we have 3 and negative 3. As you can see, let's see. Oh, we get to do some more binary evaluation, right? 1 plus 2 is 3. 1 plus 2 is 3. And then you just have that most significant bit set for whether it's positive or negative. That's really easy to figure out, right? Come on, agree with me. Yeah, it's easy. Okay, so computers perform arithmetic operations, and computers don't actually have to do this stuff like in their head like you guys did. I mean, the processors will add binary numbers in 2 machine cycles. And so that's add and multiply actually on Intel processors are 2 machine cycles. So let's see, 2 machine cycles, if your processor is going at 3.5 gigs, how long does that take to do 2 machine cycles? I mean, it's like a fraction, a very, very small fraction. So, and I remember the days. I remember when we used to actually write code and we had to optimize it. We would go through each instruction and count the number of machine cycles, and that would tell us we didn't really have very good tools back then. And so we'd actually have to count the number of machine cycles. Okay, so let's try this again. Binary addition is as easy as it gets. It's just like base 10. If you have the digits, and if you have, if 0 plus 0 is 0, 0 and 1 is 1, 1 and 0 is 1, but 1 and 1 is 0, carry the 1, right? That's all you have to remember, because you got to do the same thing you do when you add numbers now. You got to carry the 1. we'll actually talk about how they do this in circuits. You guys are all IT. I know I asked this question before. I forgot. Most of you are IT. Is that correct? How many of you are not IT? Computer engineering?
Fine then.
Okay. Okay. Just curious. So we get to that eventually. So let's take a look at this. Let's see. Now we get to do some practice here, right? So let's use sine, magnitude, binary math, and add those two numbers. Okay. 1 and 0 is 1. 1 and 1 is 1. Excuse me, 0, but you got to carry the 1, right? So then 1 and 1 is 0, carry the 1, 1, carry the 1, 1, 1, 1. Okay? What happens when you carry it over too far? Does it become a negative, or is it really an overflow? What does that mean, overflow? It means you've exceeded the bounds of that digit, or that variable, or that register, or whatever it turns out to be. Is that a common problem, do you think, in software development? Oh my goodness, I had the most embarrassing moment. Well, I mean, I had a lot of them, but I did have a pretty bad one. I wrote this podcasting software, and it was great for the big demo, and I had this big, really big MP3 file. Because it was so big, it exceeded the bounds. Each byte was being processed, so it exceeded the bounds of integers, and it would just like spin. The progress bar would go up here, and then go back, and go up there, and then go back. And like, you got to really talk. You got to be a smooth talker to get you through that. So, so it is definitely a problem when you exceed the bounds of any kind of variable or register. And really, the CPUs have something equivalent to your ints and your unsigned ints. They're called registers. We will definitely get to that in the fullness of time. Okay, let's see. Oh, we didn't have to even think, did we? Oh, there's the carry. Oh, nice. Okay, so it did what we thought it should do. Okay. So using the sign magnitude binary arithmetic, find the sum of 107 and 46. And I think we've done that. Blah, blah, blah. So also, it's just pointing out that in this case, we do have an overflow, which gives us the wrong value. Now, it could be the wrong value. It just depends on the situation. It could be the wrong value. It could be a negative or a positive number, which should be the opposite or whatever. So overflows are really bad. I think 1, 2, 3, 4, 5, 6, 7. Okay. So the signs work just like the signs in pencil and paper arithmetic. So when you add two negatives, keep them. You just add everything else. Okay, mixed side is a little bit different. So let's see, find the sum of 46 and 25. All right, so here, find the sum. Okay, which one's 46? Which is negative 25? Bottom is negative 25, right?
Yes.
Okay. So what we do is we perform those operations and we get what we get. 1, 5, 8, 16, 14, is that right? What do we get? 1,
21.
5, 8, 16. We get 21, is that right?
Yeah.
All right, so sign magnitude representation is easy for people to understand, but is not very good for those people in Intel who are having to engineer the CPUs. It's actually much more difficult than other numbering systems. It also has two representations for positive 0 and negative 0. And what that does is, it doesn't sound like it's a big deal, but it wastes that extra space. It wastes an extra value. Okay? So most computers employ a complement systems, either one's complement or two's complement. So in complement systems, negative numbers are represented by some difference between a number and space. For example, here is positive, our friend positive 3 again. And notice that negative 3 is just everything flipped, all right? Now, what's the operation that flips a bit, you know? What's the logic? Is it or? Is it and? It's exclusive or, right? It just flips a bit. You can just exclusive or these bits. One, whatever. Anyway, so the negative is just going to be the opposite. Okay? That's got to be the easiest thing in the whole wide world, right? So if you have a positive 3 and find negative 3, is that, all right, let's take a number. Let's take our number 21. It was 10101. It's 21, right? So what would negative 21 be? 0, 1, 0, 1, 1, 1, 1, right? Okay, you just fill in the rest with 1s because it's implicit that they were 0. Okay. So, what do we do about okay, so now we're using one's complement binary expression to find 48 and negative 19. Okay, so what? So we still can possibly lose that carry bit, but what it does is it rolls it around to the beginning. Okay, so if in a one's complement system, you have an overrun or an overflow that goes back to the very first bit. So it adds some complexity, but it's simpler than the sign magnitude to implement in a hardware. Okay, the hardware circuit is a lot easier. But it still has two zeros, a positive 0 and a negative 0, and you're still wasting that value. Okay. So we go to 2's complement, which pretty much everything uses now. To express value in 2's complement, if the number is positive, just convert it to binary, and you're done. That's the easy one, right? If the number is negative, find the one's complement of the number, which you already know how to do, and then add 1. Okay, so we're back to our friend 3. We find the one's complement by flipping all the bits, and then we just add 1. Okay, and that's the 2's complement. And that is what is used pretty much today in all CPUs. Motorola, Intel, etc. So let's have some fun and try this out. Here we are back to 48 and negative 19. We have a carry, and we actually end up just losing the carry with 2's complement. Okay. So 1's complement is the only thing that does that weird roll it around to the beginning and add it on. Okay. So this is the warning about overflow conditions and so forth, which I just told you happens fairly often. And doesn't matter. The only, really, it doesn't matter. You're eventually going to get a number that's too big. Like, for instance, how big are, say, RSA hashes? 128 bits, right? So that's pretty big. And what happens, now RSA has been cracked. Did you guys know that? Did you hear how they did it? They did brute force, and what they did was, some guy, it was a college instructor, and he had this lab with 24 computers, and each computer had like these NVIDIA cards, each one with like 1,000 processors, you know? And it just went for like months and months and finally cracked it. So what happens when they went to the next thing? Well, do you think the NSA is actually, that one again. Do you think the NSA is using 128-bit encryption? I doubt it. So already their numbers are getting bigger than even 32 bits, 64 bits, 128 bits. So no matter how big you get, you're still going to have that danger of overflowing. Okay. All right, that's, now, does anybody have your book? Yeah, okay. Let me borrow that. Just so I can steer you away from what you don't have to read and study. Because there's a lot of stuff in here that you don't need to look at. I would have brought my book, I'm tired of seeing them around. Okay, so in chapter 2, you've already been through .3. So this is 2.4. And what you want to do is go up through page 78 on this. So for this section, it will be enough to read page 70 to 78. And I'm going to hang out your book for the next section. I'll also talk about that too. Okay, so I got you down to 9 pages of reading, right? Okay, so character codes. Character codes. We talked about this. Originally, there were only like 127 of them, right? A, B, C, D, E, F. And really, even before like a blank space, it was like weird things like tabs, and 7 was a ding and a ding, and so forth. So there weren't very many characters. And what happened when the French people got computers, or the Italians got computers, or the Russians got computers? They couldn't type like the accent circumflex or whatever it is. You guys who are good with languages, I won't even attempt to. So what they had to do, it was great to extend it to 256 characters. That still didn't do very much good. So then they went to something called Unicode, which is a 16-bit number, which gives you 65,536 choices for your characters, okay? But characters are what we see when we run Word or go to the command prompt or surf on the internet or whatever. And they come from the early teletype machines that they used to send messages with. Let's see, and I won't ask you about BCD or BCDIC, but I will ask you about ASCII. And originally there were 6 bits. And have you ever heard that text compresses better than anything else? Like text files compress better than anything else? Have you ever zipped up a text file? It goes down just about nothing. And you know one of the reasons it zips up so well is because it's fewer bits. The old text files are 6 or 7 bits, and that's all you have to take into account. So text always would compress a lot better. So ASCII used to be the big dog until you got to Unicode, the 16-bit characters that you need for languages. So there's a program that comes from your computer called, this is not what happened. I can't run on this computer because it's totally locked. Oh, there we go. So there's a program that's on all your computers, all your Windows-based computers called CharMap, and it will show you the character set. And it always starts off, and it shows you the ASCII codes down at the bottom, and so forth. If you scroll down, it starts showing you these weird things, weird languagey things. And that's not all, because there are all of these different character sets. Let's go to, simplified Chinese. I'm going to strain right now. So these are all built into your system. So anyway, that's the short on Unicode. Except that when you programmed in C, did you guys use like printf and cout and printf, right? Okay. You were probably using all Unicode characters. Go back to it. But if you create now, this is a newer, I don't know, did you use Visual, what did you use? Visual Studio? Okay. So this is 13. I'm going to create a little C++ project here. With the mouse and keyboard, I cannot control. I need one of those big keyboards you can bang on. Okay. So even the programs you write now, you have to make a choice whether you're going to support Unicode or not. So I go here. So let's see, there should be a use Unicode character set, use multi, and if it's not set, it'll be just old ASCII. I know it should say old ASCII, but it says not set. So even now, in a simple C program, you have to make a choice of whether you're going to support Unicode or not. Totally hosed up my order of operations. So here it says that, now most of you probably have not had a Java class. Is that true or false? You had it? Okay. Did they even mention Unicode or anything? But Java supports C#. Really now everything has to support it because programming and software engineering is now pretty much international. So here's what it's available in, the number of characters. Have you ever seen Wingdings, the Wingdings font? You don't even have to have characters that you can read anymore. I don't know if I can wrong word on this computer. What's the wrong word for? Ouch. Okay, so if I go to Wingdings here. You can have 3 different Wingdings. And anyway, it's got all these really weird characters doing different things. And like music programs, they use a font that's totally has nothing to do with letters and so forth. So it has really gotten to the point where everything is Unicode. Serious. I thought I was going to talk like a lot longer. You guys have any questions? You're like, what? I'm sorry. So that's really all I have for tonight. Is that okay? Yes, sir. You want your book back, I know.
Oh, no.
No, you don't? Yeah.
Yeah.
You can get like $100 for that book.
Yeah. Oh, it makes sense.
Hey.
I tried to access your documents, but the second one.
Yeah, one it doesn't work.
Yeah.
Yeah.
Really?
Yeah, it's like you. Are you going to is it going to so
I'll check everything tomorrow. Fair enough. in the morning.
Right
now.
now.
Okay.